We're going to be discussing change extensively throughout calculus. So what we want to do before we get too far into it is actually establish what we mean by that and kind of some of the basics here so that way we know we're all talking about the same language. So let's take a look jumping in here. So when we're talking about the amount of change or the total change in terms of mathematics, we're always doing that with some value that we've measured, and we're taking a final value and subtracting from that an initial value. So if you want to think about your change in height, you take whatever your height is at the end or now, and you subtract, whatever you're comparing it to. So how much did you grow in the last year? What was your height at the beginning of the year? What's your height now? That's a change. Whoops. So then symbolically, the way we represent that, I'm just going to use x as a variable here. It's going to be delta x is equal to x minus x0 or x naught. So you'll see this as x0 or x naught, if you want a little more kind of British or European way of phrasing it, or kind of older form. This right here we call delta, and it's the symbol that we use to represent changes. So it just means change in. And an important note, delta is something we call an operator. It can't exist on its own. So I can't just have the variable, or I can't just write delta. It's not a variable, the symbol delta by itself. Whereas I can write like x by itself. X means something. Delta doesn't mean something by itself. It always means change in whatever comes after. So this would be delta y, delta z, delta a. All of those would be acceptable, but delta just by itself, not acceptable. All right, now let's talk about rates of change. So we talked about a change. Let's talk about what it means to have a rate of change. So a rate of change is how much something changes compared to another thing changing. So how kind of you can think about like which is changing faster, which is changing slower, that sort of thing. But we're comparing two changes, and that's what we mean by a rate. This means that whenever you have a rate, if you're saying the rate of blank, you need to always follow that up with respect to something else. So let's look at 3 examples to kind of make that, put that in context. So we can have the change in position with respect to time. So this is saying how much does my position change as my time changes. So every 1 second, how much does my position change? If I wait 5 seconds, how much does my position change? That's a rate because I'm looking at how much the position changes compared to how much time changes. What we'll look at mostly in this class, like our standard, will be how much the function f of x changes with respect to x. So if x increases by 1, how much does f of x increase? If x changes by 10, how much does f of x increase? That sort of thing. Now, you'll notice that this last one says the rate of change of temperature with respect to depth. So this is actually the rate of a rate. So my rate of change of temperature can be changing with respect to depth. So at a certain depth, how much is my temperature change? How quickly is my temperature changing? Well, it's going to change differently as I change my depth. So we're looking at the rate of a rate, and we'll talk much more in detail about that later, but I want to point out that sometimes your rates will be compound like this. All right, we've talked about change, we've talked about rate of change. Now we're going to talk about the one that you're going to be used to hopefully by this point, which is the average rate of change. And there's 3 forms that we're going to look at. We have form 1 right here, form 2 right here, and form 3 right here. So 1, 2, 3. This is also called a difference quotient. And that term you're going to want to hold on to because we're going to use it a lot throughout the year. It's going to come up on the AP test, stuff like that. The difference quotient you can see, because in all of these cases, it's easy to see in 2 and 3, it's the quotient dividing of two differences. So a difference on top, difference on bottom, difference on top, difference on bottom. All three of these things represent the exact same thing. It's just writing it in different ways because there's going to be different, ways that it's represented. You're going to be probably most easily grasping onto this first one, right? Final output of the function minus initial output of the function. Final x value minus initial x value. That's a rate comparing the output change divided by the input change. If I combine those using the delta terminology we've just introduced, that gives us form 1 here, which is going to just be the change in the output divided by the change in the input, the rate of change of the output with respect to the input. This third one kind of mixes that in by, if we look, how far apart is the final x value final output going to be from the initial output? Well, the final output is just going to be some position plus a change in x to get a final position minus, well, just if I didn't change it at all, and how much did I move this delta x. This one ends up being really useful for some math that we'll talk about later. If you're not quite seeing how this is a rate of change, it's easier to kind of talk through in person. So either catch me sometime in class or pause and ask about it. But this third one is the one you want to definitely be able to see how that's a rate of change. Speaking of which, if we look at instantaneous rate of change, that's going to be using that third one and say, well, let's just get those x values closer and closer together. Let's get those output values closer and closer together. So close that, in fact, they approach 0, limit as x approaches 0. And so you can think about if I've got a function, right, something like this, then what I'm doing here is I'm taking some point here, and then I'm adding some delta x and finding the new output. So if I took a big delta x and found the new output, then this would be the slope that I get when I calculate the rate of change. Now, if I take a smaller delta x, then maybe I get out to here and here, and I get a slope like this. And if I take a smaller one, I get this. And you can see the actual rate of change or slope of the function at that point is like this. And you can see as I bring these in, I get better and better estimates of my value. The second way that we can represent this is like so. And this is the same idea. It's just instead of having the delta x, I have the absolute, just the points. So I have some known point. This is f of a, or a comma f of a. And this is, say, just f of x and x. And so if I bring those f of x points into f of a, then I get the same result here. So that's our basic intro, and then as we go into the later videos, you'll see where we apply this and how we use it.